Hello guys, let's let's see about Fourier Integral and Transforms. So before studying Fourier Integral and Transforms, let's see what is Fourier Series. Okay, so Fourier series are nothing but a way to represent function. For which function? Periodic function. Let's say function fx is like this, and then again like this. So it is repeating itself in a interval of, let's say this is time axis. So this is its period. This function repeats itself after this time period t. Okay. Function value, let's say voltage, anything. It can be current, something else, pressure. So this type of function can be represented as Fourier series. Okay. And so on and so forth. uh, how to represent it in Fourier series? Fourier series is nothing but the function. Fourier said that these functions can be represented as a sum of sine and cosine terms. It is the function fx can be written as like this: a naught plus n is equal to 1 to infinity an cos 2n pi x by t plus bn sine 2n pi x by t. Okay, you can write also a by 2, that doesn't matter. Same thing, just different formula for unit. So here this is called Fourier series of this function. Yeah, but in real life not all functions are periodic. Okay, you can write periodic function as this: if plus t is equal to fx for the smallest interval t. So this is the period of this function fx. But not all function in real life are periodic. Like let's say a signal, let's say coming from space. So it can come like this. Okay, then drops to zero, no signal further than this. So how you represent this function in Fourier series? You cannot, because Fourier series is all about periodic function, but this is not periodic. This is only from time to, this is t1 to t2. So we need something to represent this so that we can analyze it. Like in engineering, there is signal processing, all those stuff. Engineer needs this, scientists need this to break the signal into simpler sine waves, like fundamental frequencies, mm, like this. Yeah, this type of signal are made up of this type of signals plus like this. So you need to find what are the components which make this, like in Fourier series. So we need a Fourier series for this. And here the condition is this is not periodic. That's the task of Fourier integrals and also transforms. Fourier integral and transform. That's the topic. Okay. So now let's revise Fourier series a little bit. Okay. Okay. So let f of x can be is a periodic function and satisfy Dirichlet condition. You can search what is this Dirichlet condition. I'm not discussing that here. Uh, that's nothing but the function is that says that the function is periodic and have a limited discontinuity. And yeah, most probably that's it. And the derivative should be continuous, and maybe some finite jumps here and there. That's it. That's the Dirichlet conditions. So if a function satisfies Dirichlet condition, it can be represented as Fourier series like this. So I'm recapping here. Let's write a. Let's find a not a n and b n here. Nx and this is a periodic function of period 2 pi. Yeah, wait. Yeah, because the real formula is this. So if t is 2 pi, 2 pi get cancelled and x will remain. That's what being written here, okay. Now let's find a naught. To find a naught, let's sorry, let's integrate this equation 1 with respect to x from minus pi to pi. Okay, let me write here. This function is a periodic function of period pi 2 pi. So integrating with respect to x from minus pi to pi, what do we get? F of x dx is equal to 1 by 2. Of course, a naught is outside, it's a constant, minus pi to pi dx plus n is equal to 1 to infinity an minus pi to pi cos nx dx plus bn minus pi to pi sin nx dx. Okay, here it will remain same. Just follow me. A naught by 2, this will be 2 pi, okay, plus this will be 0. You know the standard integration that cos nx from minus pi to pi will be 0, and also for sine. Yeah, if you see their graphs you can know why. So this is the standard integration, you have to remember it. So this is 0. So what is a naught? So 1 by pi minus pi to pi f of x dx. Okay, now let's find a n. To find let's first multiply cos mx with equation 1 on both sides. So what do we get? We get f of x cos nx. Okay, and also integrate. Okay, both side and integrate from minus pi to pi. Is equal to a naught by 2 cos, this is m, okay, plus nx cos mx and cos nx, okay, and multiply here from, integrate here from minus pi to pi dx, and the plus bn sin nx cos mx dx. So this integral will be 0. This is also standard. You can say this is a odd function, even function, odd even function, multiply, it's a odd function, so minus 2 pi, so it's 0. So now this only remain, and this is also standard, this is 0. So next step is minus pi to pi f of x cos mx dx is equal to, see, this is a summation. Summation will vary from 1 to infinity. So when n varies from 1 to infinity, at some point n will is equal to m. At that point only this integral will survive. Otherwise, anywhere else it will be 0. So this will be like, let's make it all n. So minus pi to pi cos square nx, যেহেতু sorry, like m is equal to n, because or, so this m will be replaced by n. So here an, so this is also a standard integral. This is okay, I'm solving it. Minus pi to pi, this is nothing but 1 plus cos 2nx by 2 dx is equal to the LHS. So if you solve this, only first part remains. So an will be n, the first part will be nothing but pi, and yeah, is equal to as it is. So what do you get? An is equal to 1 by pi minus pi to pi Similarly, if we multiply equation 1 with it, similarly if we multiply equation 1 with sin mx and integrate it from minus pi to pi, we can get bn is equal to 1 by pi sin nx dx, where n is equal to 1, 2, 3, and here n is equal to 1, 2, 3 like this. So yeah, that's it. We found a not n bn for a periodic function fx with period 2 pi. Those a not a and bn are called Fourier coefficients. So we can write the function in a Fourier series terms of sine and cosine. So yeah, let's try to learn another thing, the change of scale. Like we need here the period is 2 pi, but what if the period is not 2 pi but 2l? So change of scale in Fourier series. Also you can write Fourier series period for, or you can write Fourier series for periodic function with period 12, not 2 pi. Let's do it for 12. Okay, so the idea here is nothing but wait, let me add one other page here. The idea is nothing but there is a function fx which is periodic in period of 12, not 2 pi. So to find the Fourier series for this, let's use a trick. Let's convert fx to f of v, where this function should be period of with period 2 pi, and we know the Fourier series for period 2 pi. So we can write the Fourier series for fv, then we substitute back v to get in terms of x, then we can find the Fourier series for x. So the substitution here is nothing but the substitution is this: put x, whatever the function, put x is equal to pb by 2 pi, where p is the period of period of 2l, the new period here. So v is what? 2 pi x by p. Alright, so this is nothing but 2 pi x by period is 2l, so it is pi x by l. So put v is equal to pi x by l in f of x, yeah, sorry, in f of v. What does this means? When x is equal to l, because it is given that function f of x is periodic function of period 2l. So when x is equal to l, what is b? b is equal to pi. When x is equal to minus l, b is equal to minus pi. Yeah. So now f of v is f of v is now new function with period 2 pi. So we already know the Fourier series for period function with period 2 pi. So we can write the Fourier series for fv. So fv is nothing but function with period 2 pi. So write the Fourier series is this: n cos nv plus that's it. Now put v is equal to pi x by l here, f of here. Okay, we get what? F of pi x by l, or f of x, whatever you write, is equal to a naught by 2 plus n is equal to 1 to infinite n cos n pi x by l plus bn sin n pi x by l. Okay, what are the value of this Fourier coefficient? We already derived. A naught is nothing but 1 by l minus l to l f of x dx, and an is nothing but 1 by l f of x n pi x by l dx. Actually it is f of v and here it is nv, but v is pi x by l, so I already omitted the steps and writing directly 1 by l sine n pi x by dx. That's it. That's the general formula for Fourier series for periodic function effects with period 12. So now let's see Fourier integrals. So as we know, already discussed, that Fourier integral is useful for functions which are not periodic in time axis, like real life signals from any source, maybe a light intensity versus time from coming from the space or anything else. So yeah, let's uh, study Fourier integral theorem first. So Fourier integral theorem. It states that f of x is equal to 1 by pi 0 to infinity minus infinity to infinity ft is nothing but similar to f of x, just x is converted to t, u t minus x dt du. So yeah, let's prove this. Like we have seen, Fourier series is equal to a naught by 2 plus summation of a n sin n x plus b n cos n x, or whatever, or b n sin n x a n cos n x from 1 to infinity, like that. This is also the Fourier integral expansion of fx in integral form when the period is the function is not periodic. So one thing to notice here, the summation is replaced by integration. So when uh, the function is not periodic, we need lot of frequency, fundamental frequency, to make that function, so that it adds up to zero. Anywhere else rather than the specified limit. So that's why it's integration, not summation here. Unlike the Fourier series periodic function. So proof. What do we know? We know there. We know Fourier series. Fourier series of a function, periodic function, okay, f of x in minus c to c is given by what is it? F of x is equal to, as we know already, 1 to infinity n cos n pi x by c, because period is here, period is p, let's say it is to c, okay. So here p is to c, so 2 2 here, 2 n pi 2 to cancel, that's why plus bn sin n pi x by c, where you know a naught is equal to 1 by c minus c to c ft dt, n is equal to 1 by c minus c to c ft cos n pi t by c dt, and pn is equal to 1 by c minus c to c ft, okay, sin n pi t by c dt, okay. So now let's put these values of an and a not an bn in above equation here. equation let's put it equation like 2. Now substitute in equation 2, we get, what do we get? Fx is equal to 1 by 2c, because a is not by 2, ft dt 1 to infinity 1 by c minus c to c ft cos n by d by c dt. Okay, and cos nx, of course, n by x by c plus summation of n to 1 to infinity ft sin n by d by c dt into sin n by x by c. Okay, this integral is over here till here, t variables only. This is also same. This integral is over till here. Now let's solve it. Simplify. We'll get our result very soon. T dt. I'm just solving, yeah. Okay. 1 by c minus c to c ft. Okay, if you take common this term, what will be this? This term is common in both till here, huh? From here to here, this is common in both. So let's take that common and write cos n by t by c into cos n by x by c, make it bracket, sine the same term. Then dt is there, so make write dt. So now what? By 2c minus c to c ft dt plus, okay, this is nothing but the formula of, what is this? Cos a cos b plus sin a sin b. This is nothing but cos a minus b. So let's write it ft as it is, cos n by t by c minus n by x by c. Okay, dt. That's it. Or next step. So what do you see? Let's take this common, ft dt, this thing common. Let's take common. So it is nothing but minus c to c ft. When you take common, it will leave 1 here, because 1 is multiplied to this, then we'll get this first term, plus 2 will be there, because when it multiplied 2 get cancel 1 by c. So then minus, but this is gone only, the summation, yeah, only, sorry, wait, I'm sorry, the summation will be there 1 to infinity, then cos n by t by c minus n by x by c, and dt will be at the end. This whole term inside the, integration, because the variable t are present, so the integration is also with respect to t, so you cannot take it out. Or f of x is equal to 1 by 2c minus e to c f of t 1 plus 2 1 to infinity cos n pi by c, take common t minus x. So yeah, t minus x, then dt. And we know that cos is an even function. Okay, cosine function is an even function. What is even function? Even, this is extra, is nothing but f of minus x is equal to f of x. This is even. So cos minus x is equal to cos x. So cos is a even function. So the f of expression can be written as this 1 by 2c. We include this 1 inside the summation. Now we can write it like this. Wait, minus infinity, okay. Minus infinity to infinity. Let me erase this. Okay. Minus infinity to infinity cos n pi by c t minus x. Okay. So that's it. And dt. Wait. Yeah. We, for this whole term, we replaced it with this term. From minus, this is 1 to infinite. Let's say this is a number line. Here is 0. Here is 1. It was 1 to infinite and twice of it. As a cos is an even function, so you can also take this one and omit the 2. And 0, cos 0 is 1, so we also included 1. 0 here. Cos 0 is equal to 1. So everything from here to here. Minus infinity to infinity. So now f of x is nothing, or is equal to 1 by 2. Let's make it 2 pi c, multiply pi in denominator and numerator. So it will be c to c f of t pi by c minus infinity. Oh, sorry, this will not be there. Minus infinity to infinity cos n pi c t minus x dt. Okay. This is my note. I'm following my notes. So okay, now let's separate this. We write this like 2 pi minus c to c f of t. Okay, f of t. Yeah, and we take the pi by c here to here, the same term, cos n pi, so dt. So okay, this is nothing. This is a what is this actually? This is the expression of a function which is not periodic. Like let's say a function like this. Okay, any signal, let's say voltage, time is turning from minus infinity to infinity here. Okay, so we want to expand this function with this in terms of like cos and cosine and sine. So yeah, so here this is nothing but minus c, this is c. So this function is coming from is large for minus c to c. So let's make this c uh, tends to minus infinity. The magnitude of c, let's make it tends to infinity. So that what happened is the function is already 0 here. So taking c to infinity doesn't affect the expression because it's 0 here. So integral will not be 0. So it doesn't matter. So let's make the c to infinity. uh, because you know that, let's say there's a function, this function, if you integrate it from minus c to c, whatever you get, you will get same thing as minus infinity to infinity, because other other terms don't contribute to this function, other parts of the time axis. So let's make c tends to this. When c tends to this, what will be n pi? Let's put this n pi by c is equal to omega. When c tends to infinity, then what will be the next term? Like, let's n omega plus, let's say it's omega, then omega n plus 1th term. This is, let's say, nth term, omega n plus 1 pi by c. So what is del omega? N plus 1 minus omega n is equal to pi by c. But when c tends to infinity, it will be very small. So d omega will converted to d, del omega will converted to d omega. So now the integral becomes 2 pi minus infinity to infinity, the c got converted, and this pi by c becomes d omega. Remember this. So again, minus infinity to infinity cos omega t minus x d omega dt. So let's simplify further. 1 by pi 0 to infinity minus infinity to infinity, writing the terms in one, all terms combined, cos omega t minus x d omega dt. Yeah. This function okay, yeah, we assume this function is even. That's why we, you know uh, for even function, minus c to c f d anything like x, it will be same as 0 to c f dx for even function only. We did it here. So 2 got outside, 2 got cancelled. Okay, this is nothing but the proof of uh, what do you call it, Fourier integral theorem. That's it. Actually here, yeah, here it's this d omega dt will be reversed. It will be dt d omega. Oh, what? dt d omega. Here the even function is cos omega t minus x. So cos is even in terms of omega. If t is not even or odd anything, it can be anything. We don't know here. So yeah, that's it. That's the Fourier integral theorem. So now let's study Fourier sine and cosine integrals. Special case. Special case. Fourier sine integral. The Fourier sine integral is given by Fsi fx is equal to 2 by pi 0 to infinity sine omega x 0 to infinite ft sine omega t dt, okay, and d omega. And Fourier cosine integral is given by fx is equal to 2 by pi 0 to infinity cos omega x 0 to, you can put a bracket here if you want, 0 to infinity ft cos omega t dt, okay, d omega. That's it. Let's prove first one, Fourier sine integral. And then just proof. We know that we can write, this is obvious, cos omega t minus omega x and equal to cos a minus b formula, cos a cos b plus sin a sin b. Now using this expansion form integral theorem, we can write the f of x is equal to 1 by pi 0 to infinity. This is the Fourier integral theorem that we just proved now. F of t cos omega t cos omega x, just put the formula, replace this term with this whole, sin omega t sin omega x, okay, and dt d omega. All right, now let's solve it further. F of x is equal to 1 by pi 0 to infinity minus infinity to infinity ft, separate the terms, that's it, cos omega x, and put it bracket dt d omega, okay, plus 1 by pi 0 to infinity minus infinity to infinity ft sin omega t sin omega x dt d omega, okay. Now we have two different cases, because already we are discussing two cases, Fourier sine integral or cosine integral. Let's case one is if t is even function. If ft is an even function, then sine ft sine omega t odd function, okay, and ft cos omega t even function. Alright, so now uh, this formula becomes what? Let's see. 1 by pi 0 to infinity, oh sorry, it's not 1 by pi, it will be, see here, ft sin omega t is a odd function and ft omega cos omega t is even function, so this will vanish, the second term, so only the first term will survive, and omega x will take outside. Ft cos omega t is integrated over t variable from minus infinity to infinity, so it will be the two will be multiplied, and the limit will change to 0 to infinity, because it's an even function. So let's do the 2 by y. Okay, it was 1, so it becomes 2, this even function. 0 to infinity ft sine omega t sine omega x dt d omega. Okay. Wait. This will be 0. Sorry, this will be 0. Of course, this is the second term. This will be t uh, cos ft cos omega t into cos omega x dt d omega. Okay, this is it. You can also write like this: 2 by pi 0 to infinity cos omega x d omega into 0 to infinity f of t cos omega t dt, of course. And also we can write like this, put this the d omega at the end, it will be more correct. Yeah, that's it. This is f of x. So this is Fourier cosine integral. So now let's prove Fourier sine integral. When the case 2, that is when f of t is odd. So when f of t is odd, f of t cos omega t will be odd. The f of t, because odd and even function multiplied, it becomes odd function. Sin omega t, even function. Okay. So the first term now here, the first term becomes 0, the only second term survives. So let's write the second term. Second terms also we can write like 2 by pi 0 to infinity 0 to infinity f of t sine omega t sine omega x dt d omega. We can also write like this: 2 by pi 0 to infinity of sine omega x 0 to infinity ft sine omega t dt d omega. So this is nothing but Fourier sine integral. That's it. Fourier sine integral and cosine integral is over. Now let's discuss Fourier complex integrals. So what do we know from Fourier integral theorem? We already proved it in the first section. Maybe second section, and in this video, of course. We know the Fourier integral theorem. F of x. We know that a Fourier series is used for periodic function, and non-periodic function we use Fourier integral theorem. Okay, nothing new. Omega t minus x d t d omega. If you want to make it 1 by pi, then you just do it 0 to infinity, the omega function. That's it. Same thing. So now let's add something with this, because to make it complex you need something like I e to the power I or something like this. So to make e, you need to there is cos. We already know that e to the right is equal to sine cos theta plus I sin theta. So yeah, we need to add something. Let's do it. Now adding, but whatever you add, uh, let's see. Whatever you add, the Fourier integral theorem formula remains the same. So you only can add 0 actually. So let's add 0 in a different way. Ft uh, minus infinity to infinity sine omega t minus x d omega dt. dt. So let's add. Okay, now we got f of x. Actually this is nothing, just add it. Okay, adding this with f of, we got f of x is equal to uh, see why we can add, because this is nothing, this whole term is actually is equal to 0. Okay, so you whatever you add in right hand side doesn't matter, the formula remains same actually. So let's write by adding it. Minus infinity minus into infinity f of t cos omega t minus x d omega dt ft wait whatever, I used some extra bracket here, so let's use here also. So this is nothing but 1 by 2 pi minus infinity ft dt. We can take it common and multiply minus infinity cos omega t minus x uh, plus I sin omega t minus x. Okay, and at then d omega course. This is x, so this is nothing, this is, or this is nothing. You can see the right hand side is remains the same. And what is this term? This look like cos theta plus I sin theta. This is nothing but e to the right theta Euler formula. So let's write it. I omega t minus x d omega, or that's it, we proved it. This is the complex, like we have complex form of Fourier series, we have complex Fourier integral also. I'm sorry, wait, you can also write like this: I omega x. Always write the omega x term separately, there is a reason for it. Just you just now follow, we'll discuss it further. Yeah, the same thing, this is all the same thing. So this expression here is Fourier complex integral. Now let's see Fourier transform. We'll after that we'll see Fourier sine and cosine transform. Then the chapter will be over. See, Fourier transform is nothing but there is a S space like K space we have in physics. A space to, let's say, time, t space. So this is a transformation. Let's say function is given in time, so you just want to convert into a s space function, whatever the space is. I mean, to simplify the calculation, that's the Fourier transform. You can use Fourier transform here to solve like differential equation like you would do in Laplace transform. The same thing mostly. So let's derive it from Fourier complex integral formula. So from Fourier complex integral, we know the f of x is what, 1 by 2 by, we just prove it, e to the minus I omega x d omega ft omega t dt. Actually this d omega is you can write here also. Actually it is correct to write here and put this into a bracket, like square bracket maybe mostly. Yeah, this is the right way to write it. So we can rewrite this expression like also like yeah, this is the right expression. Yeah, so this expression right here, let's write in different. Let's say this is fs. Okay, so f of x is equal to, I'm sorry for the noise, e to the minus I omega x into f of s d omega. Okay, yeah, so now let's write wait, just wait. Okay, I did it. So let's uh, yeah, we can write this. Let me correct this. What? We can write now. Now let's put omega is equal to s. So the above equation you can be written like this. ds, of course. Minus infinity of t in the highest x or t, whatever. Just write t. Let's follow one. Oh, here it is x. All right. dt ds. So now using we can write this term as 1 by root pi into 1 by root over 2 pi. So using minus infinity to infinity ft e to the power ist dt as f of s in the above equation here. Okay, use this. So above equation becomes what? F of x is equal to 1 by 2 root pi minus infinity root over 2 pi, sorry, e to the minus isx into f of s ds. Okay, yeah, where f of s, this f of s is called Fourier Transform. Nothing. Transform of f of x or f of d, whatever. and f of x is called inverse Fourier transform of f of s. So f of s is nothing but Fourier of this is a when this is written this is nothing but we can write like this also, whatever your choice, like this also. This is a function operated on f of x. It says that it is transforming the f of x to Fourier transform, that is f of s. This is nothing but 2 pi. The substitution itself is Fourier transform, that's it, nothing else. I s t dt or I f of x I s x dx, whatever you can write. That's it, that's Fourier transform. Okay, this is Fourier transform. When you given a function f of x or f of t and it is asked to find Fourier transform, you just use this formula and put f of t, you find Fourier transform. So f of x can be written as 1 by 2 pi. We already have written this, I'm writing it again. Isx f of s ds. Okay, if f of s is given, you can find also f of x. So this is inverse Fourier transform. Now let's study Fourier sine transform. Sine transform. We know that also we can do it by from Fourier sine integral. What is Fourier sine integral? This is sin sx 0 to infinity. I already derived it in this video. Just go back and rewind, recap if you want. So we can write this as this. Again we split this into two multiplication now. Sine, same type of derivation, nothing new. Here also one multiplied 0 to infinity f of t sine st dt and ds. Now just nothing, just put this as f of s. We just substitute f of s, so f of x becomes 0 to infinity sin sx f of s ds. That's it. Here f of s is called Fourier sine integral. It's easy, of f of x, and this f of x is called Fourier inverse transformation of Fourier inverse sine transform of f of s. So they both inverse of each other. So now yeah, that's it. F of s is nothing but this. Let me write it clearly. So if you you are given a function, let's say f of x or g of x, you have to find the what, and you are asked to find the Fourier sine transform. So you just use this formula what I'm writing here, dt. Yeah, that's it. You just use this formula to find Fourier sine transform of a Fourier sine, yeah, Fourier sine transform of a function, and this is the inverse, of course. Now let's find Fourier cosine. Transform. So last topic probably. We already know the Fourier. This is also derived the same way. We know Fourier cosine integral. In first section we derived this. After Fourier series we have derived this Fourier integral theorem, and then we derived Fourier cosine and sine integral. You can check it. Let's write the omega at the end. That is the correct way to write it, because this is included inside the integral. They cannot be written separately. This is not iterated integral. You can study about that, where we can separately write, but here we cannot. So we have to include this term inside the what do you call integral. So both are inside each other, you can say. So you can also write like this, make it two term, that's it. Same, and put omega is equal to s. Just change it to variable changes. Nothing is new. Dummy variable. X infinity f of t. Here one means here one of the 2 pi whole root over means multiplied. Plus this 2 get multiplied to give 2 pi. So this is nothing but dt df. So now substitute whatever in the bracket as f of s. You can also write FCS here, FSS, to just signify that it's Fourier cosine transform. Just put whatever inside it, like this is inside, just put it. This is Fourier cosine into cosine transform, not into of f of t, and f of t is Fourier inverse transform of Fourier cosine inverse transform of FCS. That's it guys, thank you.